Hello everyone, my name is Matheus. I am a master's student in biomedical engineering.
And I'm Phil, a master's student in biochemistry.
You are listening to Orders of Magnitude, the science podcast exploring topics from the tiniest field particles to the confines of the universe.
This week on the podcast, we received Slater Covenden. Slater is starting his master's at McGill in mechanical engineering, where he will study green fuel alternatives.
Right. Slater was the head of research and development at the student-led initiative Space Concordia, where him and other students had the chance to work in space exploration, and Slater was specifically involved in rocket science and building rockets.
Exactly. So we discussed these student-led initiatives, but also what national space agencies and industries are up to these days.
We also talked about new space exploration projects that are happening right now, such as the Artemis project, and we had the chance to talk about fuels, metal fuels, which is his next research, as green fuel alternatives for the future.
It is very interesting. I hope you'll like it.
Have a good time.
Slater, welcome to the podcast.
Nice.
Great. Okay, so we would like to start to talk about being on a space team. You're currently head of research and development at Space Concordia, right?
Yeah, more accurately that was a period of 4.5 years or so that I worked with the team there. And it's only very recently, as in only a few months ago, that I kind of passed off the project and trained the next person because this is the nature of student societies. I went to Concordia in Canada for my undergrad in aerospace eng, and one of the first things I did, literally before going to my first class, I started showing up at, I'm going to do air quotes, but you can't see, the space lab for this student society called Space Concordia, and I thought it was great because it's all just everything space related, and spent, like I said, about 4.5 years just doing stuff there. And after a while, I kind of ended up as what you just said, head of research and development. And so I learned a very large amount of stuff during my time there.
That's a very big title, head of research and development. What exactly did you do at Space Concordia?
So I joined the rocketry team in Space Concordia. They have 5 different, let's say, subdivisions of this student society. Rocketry, which I joined, satellite, so building satellites, rovers, building robots and rovers, space health, which was only created recently, which is about aerospace medicine and health biology in microgravity or in vacuum or in space. And then 5th is special projects, so the miscellaneous category. That's stuff like high altitude balloons or specialized hardware that you're developing. And the incredible part is that nobody's paid. In fact, usually we pay to do things, but it's a student society, and it's all run by people who like space things. So, and it's not, like, I did it as an engineer. Did a bachelor's of engineering, but only about half the society are engineering, only about 3/4 are STEM related. So we have a lot of, everybody likes space. Space
Lots
is cool.
of theoretical people who don't know how to do practical stuff, and they have to build a rover from one day to another.
Well, no, not necessarily. It's because there's lots of other stuff that people like about space. You can, we host festivals. There's the Eureka Festival, which just happened. It's, not like we rent an entire area in downtown Montreal, but it's like this year it was digital just because of COVID. We usually host it in conjunction with Concordia. There's the Montreal Space Symposium, which we're part of as well. And there's a lot of non-technical stuff. There's a lot of outreach, which was a core part of what we did. So we went to elementary and high schools and just showed them, hey, kids, look at cool space things. And they're always like, oh my God, this is so cool. And then that's what I was. That's what I was when I started.
Yeah, so that's such a great initiative. And the fact that everyone is volunteer and even pays money shows that that's a big organization.
Oh, yeah.
That's
when I started, the entirety of Space Concordia was probably about 40 people tops, with varying levels of involvement. When I left, it's probably closer to 300.
300 people in these
300
5
person
divisions.
student society, maybe a bit more. depending on what your cutoff is for involved or not. But yeah, so I joined rocketry, and I spent 4.5 years in rocketry specifically. And I learned a huge amount of stuff. The head of research and development was just a title. The reason why I specifically had that title was because of a challenge that we started, or we accepted, called the Base 11 Space Challenge. Pretty simply, it's if you are the first student team to build and launch a liquid-fueled rocket to space, you get $1 million. Oh, wow. It's funded by a bunch of large aerospace and space companies and a mysterious benefactor. Literally, they're anonymous and they don't want to be known. Yeah. To pony up this big cash prize for students who make the cut and are able to launch this rocket.
What does it mean to get to space, and why is liquid fuel the milestone to be achieved?
Well, the get to space is commonly recognized as 100-kilometer altitude.
Okay.
It's not just an arbitrary definition. It's also has to do with it's called the von Karman line. Anything if you are above that without a pressurized atmosphere or a suit that protects you, your blood will boil.
Okay.
That's
scary.
Yeah, but most people think boiling my blood is super hot, so it boils. In this case, it's not because the temperature is so high; it's because the pressure is so low, and your blood will boil inside of your body, where nitrogen bubbles will just start to come out of inside of it. Now that paints a horrific image, but that's exactly why we don't go to space, and it's hard to go there, and that's
without a suit.
Exactly, and that is specifically having a pressurized environment to survive that you have to generate in your vehicle or in your suit to survive above 100 kilometers.
Oh.
You below that, between let's say 10-kilometer altitude and 100-kilometer altitude, you definitely need an oxygen. You need to bring your own breathing gear, but the pressure alone will not cause you to just die like that. Mm-hmm. So, there we go. Mm-hmm.
So the goal was to put the rocket in space. It didn't have to necessarily stay in orbit.
Going to space and orbiting are two entirely different ball games.
Let's just.
It's an order of magnitude harder. Let me tell you. See, I can drop the name podcast a lot in this. But so going to space is basically you have to be able to launch a rocket that makes it above 100-kilometer altitude and returns. And you have the stipulation is you have to recover it, as in you have to be able to find it, bring it back in one piece, and reload all consumable materials, in theory, including fuel and oxygen, and launch it again. It shouldn't just be a one-time thing. That's part of the stipulation of the competition, is that it's liquid fuel. Your fuel has to be liquid form, and that's important for other reasons I'll tell you after if you want. But it also has to be recoverable, which is even more harder.
That's really interesting that they ask students to do that, because SpaceX was struggling with that not too long ago.
Well, SpaceX wants to go to orbit as well. I'm not going to lie to you, it's an absolutely insane challenge, and there's a reason why there's a big prize and not many people have made it very far. But the intention of the challenge was to pipeline future space talent, meaning you want to have a generation of people in this competition was specifically in North America. It's US and Canada only. People, engineers, technical people, STEM people who have direct experience with space and space tech that most university graduates, in fact, pretty much no university graduates have at that level. In finding the technical expertise or training someone to build a rocket is very hard. So the point of this competition was to create a generation of people who did have those skills so that you can use them to do great things. That was kind of the idea behind it. Mm-hmm. So that's
because, you said, student-led initiatives, most of the time the generations are about 4 years. So you need every 4 years to have a completely new set of completely trained students. And it's hard to have that first set of students who have the skills. to build a rocket.
There is a continuation effect after that, but it's remember how I said the liquid fuel rocket was the hard part? So student teams have built rockets that have gone to space before. This has happened. But all of those rockets have been using what you call a solid motor. So a solid motor is kind of like a giant, really explosive candle. You can also buy them. I mean, once you get past a certain power point, you need special permission to buy them, but you can buy them. They are manufactured items that you can load into the back of your rocket, light, and it just...
It's like a firework. Basically.
Exactly. It's literally a firework, but except you don't want it to explode at the apex. But that's the thing. So you can purchase these solid rocket engines, and it's what you do for model rocketry. It's what you do if you want to make your own fireworks, all that jazz. But that's why liquid is so hard, because liquid engines are, on a technical level, I'm going to say it again, an order of magnitude harder than solid rockets. And the altitude is also makes it a very difficult challenge as well. The three most difficult things about it are it has to be liquid, liquid fueled, it has to be recoverable and reusable, and it has to be minimum 100 kilometer altitude with your flight. And those three things are really like the most difficult parts of achieving, because
the recoverable part must be
they all come with their own associated challenges, and the recoverable one is definitely one of them. So yeah.
So we'll be talking about fuel a little bit later, but why is liquid fuel specifically harder than having a solid motor?
So solid motor is, like I said, kind of just like a really explosive candle. It's solid in shape, and you literally just can hold it. It's like a big tube, a giant tube. It can, bigger the tube, the more explosive it is, but that's the gist of it. You stick it in the end, and you can light the end, and it will just fly off. Designing a liquid rocket engine from scratch is a very difficult technical challenge for a few reasons. First off, you have to design and build very high pressure containers, tanks, to hold your fuel and oxygen. So in a solid rocket motor, your fuel and your oxidizer, the thing that you mix to make the boom happen, they're already in solid state, and all they need is a spark to start. As in, you already have your fuel and your oxygen pre-mixed, and you can just burn it like that. With liquid, you need at minimum 2 separate tanks, one for oxygen and one for fuel, because having them in the same tank is a bad idea.
Basically, as soon as they will come in contact and have the right amount of energy, they will explode.
I mean, that's what they're meant to do, yeah. That's basically what happens. But the thing is that it's possible that what you can do is pour them into the same tank, and they're not necessarily going to immediately explode, but it's just very likely, and it's not a good thing, and it's going to explode. Also, usually your fuel and oxygen have to be stored under different conditions. Usually one has to be pressurized at a different state, and one has to be really cold. Usually your oxygen has to be very cold, and your fuel can be room temperature, but maybe higher pressure. So you need 2 different storage environments inside of your rocket to do this. Now you have there's lots of different combinations of fuel and oxidizer that bring their own specific technical challenges, but another general one that applies to all liquid fuels is that you have to manipulate and handle them inside of the rocket in a compact, efficient, very lightweight, very secure, very reliable manner. Your piping and plumbing system, the one that we spent a long time iterating on our piping and plumbing system on the inside. So our choice of oxidizer was liquid oxygen, for many reasons that are very difficult to describe, but basically that's what we chose. Now, liquid oxygen is lovely because it's extremely dense in terms of energy per unit volume and per unit weight. So it's very good to have on a thing you want to fly high. But the problem is that you need to store it at minus 160 degrees Celsius or something like that. Very, very, very cold in order for it to maintain liquid state.
So it has to be far away from the ignition, far away from the...
So yeah, it had. So for example, our oxygen tank was on top of the fuel tank, and then below the fuel tank was the engine. So you have a distance of separation. But also what that means is storing something at 100 minus 100 something below, almost minus 200 degrees Celsius,
That's crazy.
is very difficult. You have to maintain it at that until launch, and usually your pipes on the outside will gain a layer of ice and encrustment. If you've ever seen a photo of the shuttle launch, you'll see a bunch of ice falling off the exterior tank. That's what happens. It's so cold it just freezes the air on the outside.
And is it with liquid nitrogen? Is it with another substance?
To cool it?
To cool it down.
So there is no onboard cooling system. What you do is you fuel the rocket, and then immediately upon finishing, you detach and you have to launch. Otherwise, it's all just going to boil off.
Whoa.
So that's why when you see the Saturn V or big rocket launches like the Apollo missions, you have these towers, these cranes that detach right as it launches. Because it's filling it up until just the very end. And then it's done. Okay. Detach and then...
Wow.
That's insane. So the countdown is basically the count up of the fuel filling up.
Yeah, exactly. And then, you fill up the oxygen for a huge rocket. It's God knows how many hundreds of thousands of liters of fuel and oxygen. And, in the time you start pouring it to the end, some of it's going to boil off. So you're going to keep needing to fill it up. You're going to waste a little bit because of the nature of the fact that,
It boils.
ambient life is not minus 170 degrees Celsius or whatever it is. But yeah, so those are, some technical challenges that come with using that's just one example of oxidizer, which is the most common one. It's usually just liquid oxygen. So there are other options like nitrous oxide or that's laughing gas actually, or other gases that have an oxygen, like an oxygen component. You could use air, but you're carrying a bunch of nitrogen around in the air as well. So the boom component is the oxygen.
There is less density, I would suppose.
Yeah. You want to be as efficient as possible in terms of energy per unit weight and per unit volume. So there's all that jazz. But yeah, so suffice it to say, it's very hard. Now,
it's rocket science.
It's literally rocket science.
Yeah.
I get to use that phrase a lot sometimes. It's fun. Come on, it's not rocket science, but yeah. It's hard. It's really hard. It's like stupid hard. Like I didn't understand how hard it was. I still don't.
Yeah, but it's really cool that even though it's super hard, like the advancements that we've made so far in space exploration with the new Mars rover that just landed,
Curiosity, and then this current one is
Dragonfly or something like that.
Well, no, that's I don't know if that's the actual name of the flying robot on the underneath, but there was Curiosity was the most recent one. I forget the name. Right. I know I can see it in my mind, but I don't remember the name.
It ends with a Y also, I think.
Oh yeah, definitely. But yeah.
Is there any new space? I imagine you're following the space exploration and all rocketry stuff that is happening right now. You follow that media?
Oh yeah, I'm not like every day, but yeah, I kind of like keep in the loop of what's going on.
Is there any project that is happening right now that you're especially excited about?
Okay, so I went to this conference called the International Aerospace Conference, International Aerospace Congress in Washington, D.C. about 2 or 3 years ago. There, it's kind of like a gathering of a bunch of space government agencies, nonprofits, and private corporations. So during the opening speech, there was, at the time it was Sid van der Pelt was the head of the CSA. There was also the head of the Japanese Space Agency. There was the head of NASA. There was the directors of the European Space Agency and CNES, which is the French one. And there's the German and British representatives too as well.
And for the listeners, maybe they don't know, CSA is the Canadian.
Oh yeah, sorry. The CSA is the Canadian Space Agency. They have a headquarters right outside here in Montreal, just like in Saint-Hubert, like an hour drive or so from here. But yeah, so what they introduced was the, let's say, next step in the big scale. What are they doing for space exploration? So the United States, NASA's budget for space exploration is much larger than most other national space programs put together. We're not talking about just private space exploration currently. We're talking about just public space agencies. NASA's budget is much bigger than pretty much most other agencies put together. So what they do guides a lot of other people in direction and technical choice. So what they have decided to pursue is something called the Artemis Project. The ISS, International Space Station, is nearing the end of its design life cycle. It's been up there.
Which is supposed to finish in?
Well, that's the thing. You design it for a certain time, but how long can it actually go for? It's usually a lot longer if you design it. So it's not so much there is, a technical limitation on how long do certain parts last, but it's also a political alliance, really. The agreement between the United States and Russia to maintain this incredibly complicated piece of hardware that's floating around space. And they've done it in a spectacular fashion for the past 20-something plus years. There's been continual human presence in orbit for the past 20 plus years. Almost, I think, just as long as I've been alive, which is about 23 years. So that's, to me, an incredible diplomatic mission, but there is both a technical and a diplomatic constraint on how long this can actually be up there. Everyone knows that at some point it's going to come down. Exactly when hasn't been decided yet, and it's when they do, it's basically like, we did this experiment, and ISS is actually, it's a floating laboratory. That's really what it is. It's a laboratory to test stuff out. It was and still is a massive experiment in what does it take to survive in space? What effect does it have on the human body? How can we recycle as much as we can? What are the negative effects of prolonged space exposure? What effects on God knows however many experiments they run up there.
Yeah, I've heard about the bone density problem and the fact that when you're in 0G for too long, your bones become less dense and then they can break spontaneously when you go back on
Absolutely. The human body responds to a lot of stuff. And in the case where you are floating around, you don't need your skeletal system as much. Your bones don't do what bones do, which is support your body from gravity. So if you spend extended periods of time up there with no intervention, your bone density will decrease, almost as if you have osteoporosis. And upon return to Earth, you can break your bones. However, that's the whole point of what that was. Aerospace medicine, that was one of the big problems associated with space travel or long-term space microgravity exposure is, lowered bone density and a shit ton of other health problems. But something that can be done to anneal that or make it less bad, like the bone density dropping, is heavy resistance exercise. There's actually an exercise room on the ISS they don't have weights up there because weights don't mean anything in microgravity. Instead, they have resistance. So it's just like an elastic band, or I believe in their case, it's like a gas piston or something that's not heavy. It provides resistance being pulled apart or pushed together. And this allows them to perform heavy exercise in high force exercise. And there's a very, very strict training regimen you have to observe when you're an astronaut in space to avoid losing as much bone density as possible. So that, it's one of many other discoveries, along with diet and exercise and
radiation, I suppose.
Radiation. Well, that's why the ISS is at a relatively low orbit. It exists in what you call low Earth orbit, or otherwise known as LEO, L-E-O.
What is still protecting the astronauts at this orbit?
It's more protected than completely out of the atmosphere.
Is it an ozone layer still?
The ozone layer exists at higher levels in the atmosphere, above it, and it's not just. I'm not an atmospheric scientist. I couldn't tell you exactly let's say how dangerous it is to exist at what point, what exposure you get depending on what level. but while you still are within, while you're still below the, let's say 100 kilometer to 60 kilometer range is what you call the ionosphere, or actually don't quote me on that, but there is a section of the atmosphere, an upper layer called the ionosphere, which is heavily charged and helps disperse a large amount of cosmic radiation. So being closer to the planet, lower in the atmosphere, you get less exposure. So of course, that's part of what's being studied, but is dangerous. So it's it's not quite a death sentence to say, hey, expose yourself to cosmic rays. It's more like we know it's really dangerous.
It's like getting a few X-rays in your year on the space station.
Well, see, that's the thing. It's not everyone's. A lot of people are scared about cosmic rays. They're gonna turn me into the Fantastic Four or whatever. But it's really dependent on real exposure. So, a lot radiation is a scary term in a lot of people's minds, and I understand why, but given media and sensationalism, but unless you know what radiation dosage you receive, you really can't tell what's going on. For example, bananas are radioactive. You receive radiation dose from eating bananas.
Yeah, it's the biggest dose of radiation for most people when they don't go to the dentist too often, actually.
Yep. And it's stuff like that. So it's really dependent, and I don't have the exact numbers off the top of my head because
let's get out of the nitty gritty.
Well, no, it's fine. Yeah, it's okay, but so it's really dependent on your exposure. That's it.
But we were saying the ISS, an amazing lab, the diplomatic project that is amazing between the States and Russia. You were mentioning, and you were actually talking about the Artemis project. Is what you wanted.
Oh,
to
sorry,
to
right.
tell us
I got
about.
completely distracted. Okay, Artemis project. U.S. has a huge budget. What they do kind of sets the scene for what other agencies and even private corporations want to do. The direction that NASA has chosen to go in the previous, let's say, 6 decades, was we're going to make everything ourselves. It's going to be goddamn perfect, and it's going to be stupid expensive. But you better bet your butt it's going to work. And it's, with the exception of very few very small technical challenges, most people have heard of the Challenger shuttle disaster. That was actually a political issue, not a technical issue. Fun fact. The reason why it exploded. Anyways, the Artemis project is their attempt to combine private space exploration and setting up infrastructure. What they want to do is they want to return to the moon in a more permanent fashion. What they want to do, they want to create the Artemis station. I don't actually know if they're going to call it the Artemis station. It's just called the Artemis project. They want to put a station in orbit around the moon. It makes sense as a stepping stone as our nearest celestial neighbor by an order of magnitude. Ha 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 ha. And it provides a staging platform for further exploration, moon study, Earth observation, and a great location for a stepping stone to outer space.
Why in orbit? Why not set up foot underground and have buildings on the moon? That's
the thing, it's easier to put something into the orbit and then build on the surface than to just go and try and build on the surface. It's a stepping stone, right? So it's not that they're not going to build on the moon. It's that it provides a very good infrastructure for getting to the surface or getting further.
I would also imagine that if you want to leave, it's easier to leave on orbit than to launch from the surface of the moon.
Yeah, I mean, if you want to leave from the surface, there's an energy cost associated with it. It's on the moon, it's a lot lower than on Earth, but there's still an energy cost associated with it. So, and this isn't to say that you can only orbit the moon or only exist on the surface. It's that the easiest thing to get, it's harder to land on the moon and leave than it is to just orbit, than just to go orbit the moon. But what specifically about their strategy they've chosen to do is, instead of NASA saying, we're going to design everything from scratch and make it perfect and cost $400 billion. No, I'm joking. That's not actually the stat. It's not a real, I'm exaggerating.
Okay. Yeah.
It's not about an order of magnitude.
It's not $400 billion. Their budget was recently increased to something about 10 billion, which sounds like a lot, but in the order of percentage of US GDP, it's actually quite small. And they're using their budget to contract private companies to build parts of their systems. So they are encouraging private corporations by using their by requesting that they and contracting them to build these highly complicated, very difficult pieces of equipment, they build that expertise. And also, you get contracts, you build your space side of your company if you have one, you can encourage launch vehicles, you can build satellites, all that jazz. But let's say, for example, one company builds just the pod that houses humans in your rocket. They're building the Space Launch System, which is the most powerful rocket since the Atlas V, which is Saturn V, the one that brought us to the moon. Because, you need a big one to go to the moon, right? So the current option for going up to space is the Soyuz. And there's a bunch of other ones, but the only ones that so far have reliably done human travel for a long time were the Soyuz. There's other ones that are in development, but the Soyuz rocket run out of Baikonur, Kazakhstan, by Russia, is the one that has the most flight heritage. The last U.S. flight program was the shuttles, and eventually they figured out it was just cheaper and easier just to use the Soyuz, the rocket that the Roscosmos, the Russian space agency, uses.
What about the Dragon?
The Dragon capsule? Yeah, like that's an example. Like I don't know if NASA contracted them specifically to build the Dragon capsule, but that's an example of what I'm talking about. You have private companies that are now building these space hardware. It's not that what I was saying is that specifically rockets that have decades worth of launch experience. It's not that there's no rockets that can launch humans except for the Soyuz. It's not true. It's that only the Soyuz has decades of flight experience, and in aerospace, flight proof testing is king. No amount of math, no amount of testing on Earth, no amount of anything compares to showing that you can launch it and recover it.
To having the data that you sent people into space and they didn't die to have the stats. So
look,
you're not going to die. You're likely not to die.
Exactly. Listen, we can show you statistically that there's a 90-something% chance that our rocket's not going to explode on launch. We've done this, let's say 300 times. That is invaluable. That is, I would say, worth its weight in gold, but it's a concept. It's more valuable than any form of analysis you could possibly do. Showing that it works, that's it.
Does that put some brakes on the innovation, that way of thinking?
Well, we're at a very particular point in tech development history for space exploration, where for the past, century, I want to say, it's been all for space exploration. It's been heavily funded by public agencies. And this occurs in a lot of things where it's not something that's profitable. At least only now is it starting to be profitable. NASA and the European Space Agency and JAXA and Chinese Space Agency, all these public space agencies are developing technology and have been developing this flight technology for the past 60 years, decades of worth of energy and time and money. And now we're at a point where we have, as a species, a decent amount of experience with launching shit into space. It's not perfect. It's still very, very hard, but at least we've done it for a little bit. So the tech has been developed, and now private corporations are kind of jumping on when if they can throw huge amounts of money at the problem, and their approach instead of public space agencies is, instead of making it perfect, we're going to go for a fly launch crash kind of, or I think there was like fly crash, whatever. Like SpaceX has launched however many goddamn rockets, and most of them have exploded, but this allows you to iterate really fast using technology that's been developed in the past 60 years as a base to go on and throw money at it to develop and iterate faster. Because NASA that's not their philosophy. That's not their design philosophy. Private corporations sponsored by very wealthy individuals or whatever can choose to make it this way. And that's the new paradigm, let's say, of their choice of how to do it.
This is this brings to my mind, this is a very spontaneous subject that just came to me, maybe polemical a little bit. It seems like there's a lot of money. that is being spent in space exploration.
I think I can tell what your next question is going to be.
This money, don't you think it could be used in other things that seem a little bit more urgent?
Very, very good question.
Such as, I don't know, human health or...
We always hear this, why do we want to go to space? We should rule out our problems on Earth before and then
I think
go to
it's a
space.
very legitimate question. As someone who's studied this and seen the amount of money that flows around sometimes, I think it's a very legitimate question why you would ask that. Now, your answer to that really depends on your perspective on it. There's the one camp, which is kind of like, we have human, ecological, very real, concrete problems that can be solved with money that we here on Earth. Then there is the other side, which is space exploration is the future, and overall, that is the, let's say, the next step, if you want to call it that. You can choose to believe that. I don't think that I fall into either of these camps per se. I have a slightly different take on it. I had that exact same question, and often when people ask me that, my usual response is, well, okay, how much do they spend on the space program? And most people don't know. And I feel like asking someone that is an unfair question if I myself don't know. So a while ago, prior to in the early Obama administration, I don't know what year that was. I was about 16, so that's probably like 8 years ago. 2016-ish, 2015, something like that. I looked up and put together a chart of what is the public space budget of all these public space corporations. And then I didn't do private space corporations at the time. They weren't as big at that point. But the U.S. budget for public space agencies, I compiled and put together. U.S. budget, and then the next biggest, I think, I don't remember who's the next biggest, but the large ones are the U.S., Russia, you have European Space Agency, JAXA, India, China, Australia, actually, Canadian Space Agency, and other ones like the UK, France, Germany. Putting them all together, stacking them up, turns out that internationally, in 2015 or so, the combined world spending on public space agencies was a fraction of the Canadian federal social spending. This does not include provincial social spending. So it was on the order of something like 15 or less % of this. So that means that internationally, in 2015 or so, you were only spending 15% of Canada's federal social budget. So social budget is vague, of course, but that's what they defined it as in their budget. So that's what I was going by. They had large categories, but social included healthcare, employment insurance, and a host of other social benefit things by the federal government. And this is just Canada, just the federal government, and just the social expenses.
A fraction of a fraction of a fraction.
Mm-hmm. It puts it into perspective that it's not like, oh, it's a ridiculous amount of money. To the average person, when you say million or billion, yes, it does sound like a lot of money.
In your bank account.
Exactly. Because that's what we're used to. That's what we're used to. But in the grand scheme of the world, it's actually tiny. Now, that was 2015. In a few years after that, NASA's budget got multiplied very large, up to what I said before, which is about $10 to $14 billion. I don't know what it's at this year, but that's what it was a few years ago. So that's a lot larger than it was before. Also, there's a large amount of private space interest. But who are you to tell individuals what to do with their money? You can, but legally, you can't do anything. So it's not about what you can do. It's kind of like, usually the question is, should we be doing this? And the answer, like I said, kind of depends on what camp you fall into. Is it the exploration, or is it the real concrete problems? My answer to that is that I wish that there was a good way of knowing how to apply this money in a reasonable way. If you could just take all the money that was being spent on it and use it to directly solve social problems, yeah, that's really good. But let's say somehow magically, the government had access to this massive flow of funds from all these private space companies, and mostly being supported by very wealthy individuals. Musk and Bezos and other people come to mind. If all that money that they threw into other companies instead went to the government, how would the government spend it? If you could guarantee that all of that money was spent in a efficient and concise way on these problems that you want it to be spent on, then yeah, there's a very good argument for that. But how are you going to do that? There is the not just technical, but the political challenge of being able to do something like that. I'm not saying it's impossible. I'm just saying that it's not as simple as we spend it on this or we spend it on this. There are many more layers of difficulty between applying money to this problem and applying money to a social problem.
And that's not even talking about the political fact that we can have our cake and eat it too by taxing them more on the rest of the money they have. But let's not talk about this.
I mean, taxation policy, I'm not an expert on. I will not comment. But my point is, it's really not as simple as just saying take the money we used to solve this problem and instead use it to solve this problem. On the surface, of course, like, okay, money solves problems, we can use it to solve this problem instead. I understand why it's thought that way, but it's really not that simple. Is it possible? Well, yeah, in theory. How likely is it to happen? Not very likely. That's my answer.
So here's a very good transition to a next topic.
Yeah.
We're saying there's all of these problems, it's either space exploration or some other more urgent problems that we have here. One of the urgent problems that we have on Earth is global warming.
Yeah.
All the environmental problems that we have. But some of the money that is being spent is spent on research for what we call green fuels. Right? And I imagine that's what your research will be about when you start your master's next year.
So I am going to start my master's degree, Master's of Science at McGill, in mechanical eng, and my field of research is going to be green fuels, like you said. Specifically, the term that they use is alternative fuels, but it means kind of the same thing. I will be researching non-carbon based fuels.
Can we start with the very basic of what a fuel is and what it does?
Oh yeah, absolutely. It's very important. So when you say fuel, most people think gasoline, and that's very accurate because it is a fuel. What is a fuel? A fuel is anything that carries energy. You can extract that energy later, and you can carry it with you. And normally, but not necessarily, a fuel involves you burning it. So oxidizing or combusting it in your engine.
So you bring something with you that has energy in it,
and
then you lose it while you're going.
You burn it to go further. Exactly. Now, this is a very specific definition because batteries fulfill all the criteria except for combustion. So batteries are not a fuel because they do not burn per se.
Could we have a big lithium-ion battery, stick that in a rocket, and somehow get it to lift off?
Currently, no. There is no engine technology that exists that can transform electricity into thrust that is high enough to launch from Earth. However, in space, using electricity to drive what is called an ion engine is the most efficient engine for deep space travel that we have ever. It's the highest efficiency for long-term low thrust applications that we have. And it runs off electricity, not burning, electricity.
Okay, so basically we need fuel because the fuel is the only one that is able to produce enough thrust. Whereas when we have an electric car with a battery in it, we're able to produce enough energy in order to propel the car. Yeah, forward.
Batteries have a very large and wide, very good application. Heavy lift rocketry is not one of them.
Okay, you need a lot of output in a very short amount of time.
And it's not even about the energy discharge rate. It's how do you transform this electricity into kinetic motion? And there's no rocket engine that does that. You can have propellers, or you can have helicopter blades or something like that run on a motor maybe, but that tech does not exist currently. We don't have, it doesn't exist at the level. Also, even if we did have an engine that was able to take batteries' energy and transform it into motion in a rocket way, the energy density by unit weight of a lithium ion or even very efficient batteries is actually quite awful. It's actually really bad.
Okay. Can you talk a bit more about these ion
engines?
These ion engines in space. That seems very, very interesting.
Yeah, so fundamentally what a rocket engine does is transform stored energy into kinetic energy. Now, that's what most engines do. Your car engine turns the chemical energy of your gasoline into forward energy motion using mechanical means. Rocket engines usually are defined that they produce thrust, meaning you are pushed forwards by things going out your butt really fast. Mm-hmm. If you fart, that's technically not sort of a rocket engine.
Some amount of thrust.
Yeah, exactly. It's minuscule, but it exists. You throw gas out the back really fast so that you go forwards because of conservation of energy or momentum. So that you throw mass out your back, so you, the thing that threw it, goes forwards.
Third law of Newton.
Yeah, exactly. For every action, there's an equal and opposite reaction. Throw something back, you go forwards. So that's it. Now, the faster you throw it out the back, the faster you go forwards, which is why the gas that comes out of rocket engines is really, 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 really fast. So that you're shooting gas, which is a not very dense, to lift a solid metal object. You have to throw the gas very fast to go up, right? Mm-hmm. That's why rocket engines shoot out gas so fast. Now, you have to get a lot really fast, going very, very fast, to go up. And that's why rocket engines do what they do. You burn and burn and burn to go higher into the atmosphere. Now, a rocket engine, what people normally think of is you mix a fuel and oxygen, it explodes and produces high energy gas that flows out the back. Ion engines work under a fundamentally different principle. Mm-hmm. In a regular rocket engine, you have your oxygen and your fuel that you mix and burn to produce high velocity gas that's thrown out the back. An ion engine uses something entirely different. There is no combustion, there is no oxygen, there is only a fuel. Now, you might say, why do I have a fuel and no oxygen? It's because it's not a fuel like gasoline. It's actually a gas. Normally it's xenon or neon, a noble gas, mm-hmm. a inert gas. And what you do is
a gas that is not supposed to react. Even if you put oxygen, you throw it at it.
You cannot burn it.
Okay. In the case of hydrogen, which is the most common fuel, I think, when you put oxygen and hydrogen, a little spark, they will burn.
They burn quite explosively. Okay. They burn very well. But a noble gas like helium or neon or xenon will not burn. It's almost impossible for them to burn. Only under very specific conditions where you force them to dissociate in very specific ways can you even attempt to burn them. So they are incredibly neutral. They react to nothing. They're called noble because they don't like to be involved. At least that's what I think. But anyways, so an ion engine uses a gas that doesn't react to anything. How are you going to use that? Well, what they do is they use something called, they have a big voltage difference in your engine. You have a very strong electric field that you generate with electricity in your engine. And what you do is you send this inert gas, very small amount, through a small tube, and during that process, you use a very specific induction coil, a very specific electricity coil, to ionize it, meaning you can charge it negatively or positively. So you have this electrically charged gas, which you then send into your electric field that you've generated. It shoots it out the back really, really fast. What you have is gas that comes out of your butt really fast. You have generated gas that moves fast without explosions or oxidation or combustion. You just have an inert gas that you've charged that you use electricity and electric field to shoot it out the back really fast.
So just to summarize what you just said, it's like making some very small positively charged marbles and putting them in an electric field so that they're shot out of the butt of the engine.
Exactly.
And because of that, the rocket just goes forward.
Exactly.
And why can't we use that on Earth? What is the difference?
There's atmosphere on Earth. In order for you to ionize these particles and shoot them through a electric field effectively at an efficient manner, there needs to be no atmosphere. Means that there can't be any oxygen or nitrogen for it to bump into. You can't have air particles for this thing to hit because it's gonna be absorbed and slow down.
Yeah.
So as soon as they would come out of the electric field, you would have some friction with the air and you will lose the ability to move forward, or what?
Yeah, something like that. But basically basically what you're doing is you have highly charged particles that you're trying to throw out your butt. If you have air inside of this place where you're trying to do it, it heavily impedes the motion you're trying to get. So that's why. Also, one of the great limitations of ion engines is that they produce very low thrust, but they are the most fuel efficient engines we have ever discovered. They are orders of magnitude, I said it again, more efficient by let's say amount of fuel you have to carry versus how fast you can go in space. They are so much more efficient over long missions, long duration burns.
I imagine that's because of the small tube, right?
Exactly.
Every single atom is made into a positively charged atom and goes out exactly in a straight line.
Very straight line. And the individual particles travel so much faster than regular gas combustion particles would. So remember I said the faster you throw out your butt, the faster forward you'll go? Well, it's not just how fast you throw them out, it's how fast do you throw them out multiplied by how much do you throw out. So in the case of ion engines, the actual amount that you throw out every second is very low, but the speed at which they're going out your butt is really high. So it's extremely efficient in terms of amount of mass, amount of fuel you need to carry with you in order to get to Mars, let's say. But or even further, the longer duration burns they are, the more effective they are. The way that rocket engines are classified, let's say in terms of efficiency, one common metric that's used is called specific impulse. Basically, it's how much oomph do you get for amount of fuel that you use. It's similar to miles per gallon. Think of it that way.
Okay.
Yeah, or kilometers per liter.
Basically, the efficiency of a fuel.
Basically, yeah, and not just the fuel and the engine, but because every engine has a different design, so you get a different one. And the specific impulse, the higher it is, the better. And the highest specific impulse engine designs we have are all ion engines.
So let's get back to.
Can I just get some numbers before?
Yeah.
I would really like to know, like, what is the efficiency of an ion versus the efficiency of using hydrogen and oxygen, for example?
The highest specific impulse, highest efficiency, let's say conventional chemical rocket engines we have are maximum like 600 seconds. Now, the unit of specific impulse is in seconds. I could explain to you why.
Don't ask me why.
But
Give me the number.
It's complicated. It just has to do with unit analysis. It's a semi-non-dimensional parameter that's used to just characterize engines, meaning
whatever that means.
Yeah,
this is why it's called rocket science.
It's a measurement. It's a measurement of how efficient a rocket engine is, and the reason it's in seconds, there is a very good explanation, but I don't have the time nor the visualization to offer you this explanation. Do you understand?
Yeah.
But so the highest efficiency chemical engines we currently have are around 600 seconds. An ion engine can achieve easily 1200, so 1200 seconds, at least twice, even more, perhaps 6,000 seconds of ISP.
6,000 would be an order of magnitude away.
It would be about an order of magnitude.
Man,
exactly.
we'll not get the chance to say the title so many times.
So here's the thing. Efficiency of your engine dictates how much fuel you have to carry with you. The more fuel that your rocket has on it, the heavier it is. So the more fuel you need to launch.
Yeah.
So that means you need to put more fuel in it. So you get heavier. So you need to put more fuel in to carry that extra fuel.
So there's an optimization problem.
There's a compounding effect. Actually, there is no even optimization problem. The optimum thing would be to carry no fuel and have infinite thrust. because that's the perfect, but that's of course impossible. But what you want to do is you want to carry, the more efficient your engine is, there is a compounding effect with your fuel. You have to, let's say you have an efficient engine, you switch to an even more efficient engine that uses the same fuel, for example. The amount of fuel you have to carry goes down, and then you get lighter, so you have to carry less fuel. So you get lighter, so you can carry less fuel. So you get lighter, so you can carry less fuel, because the fuel adds weight to your rocket.
That sounds like it needs an integral to be solved.
It does, actually. But yeah, the point is there's a compounding effect. Every single weight savings you get saves you even more once you remove the fuel that you need to carry that weight. So that's equivalently why adding weight is so bad. Because if you add weight, you need more fuel to carry it, meaning it's heavier because of the fuel you put in, etc., off till the horses come home. Mm-hmm. And that's it. Mm-hmm. So there we go.
Oh, wow.
Extremely cool. Now let's get into your future research.
Thank you.
Which are metal electro fuels. Is that it?
Electrofuels. Hell yeah. So before we mentioned green fuels, I'll tell you now, there's basically only 3 options that we have so far for fuel that is not carbon based. First, remember what I said about fuel, which is that there's a few key characteristics. It means that it's oxidizable, meaning you can burn it. You have to be able to burn it. Number 2, you're carrying it with you. Number 3, it's a store of energy. So your green fuels would have the additional condition that you don't burn, there's no carbon in there, so that it does not emit CO2. Carbon dioxide is one of the major components of greenhouse gas, which is most contributes to the greenhouse effect and global warming. So a green fuel, ideally, would not release any carbon dioxide. Now, there's not many options that we have that do that. There's only 3. So you mentioned one of them, which is metal powders, which is the most esoteric variety. Second, that most people know about is hydrogen. Hydrogen is a fuel that does not produce any carbon dioxide because there's no carbon in it. It's just hydrogen. And then the third option is ammonia or ammonium. I believe it's ammonia actually, but
NH3 and H4.
Exactly.
And H3 is ammonia. What?
Something like that. But the point is that these 3 do not emit carbon, but they all come with their own they all come with their own challenges, and technical or otherwise. So I'll tell you now, there is no perfect solution. Most people are looking for, or think that we're looking for the ultimate fuel, the thing that emits no carbon, it's perfect, we can carry it with us, it's efficient, it's the densest, whatever. There is no such thing. There is a time and a place for the application of all different technological inventions, not necessarily, I'm saying in terms of their effectiveness. So all fuel choices have upsides and downsides. Gasoline is a very popular choice for multiple reasons. It is available. It has a very high energy density. It's relatively neutral. You can store it for, when I say neutral, I mean like it won't spontaneously explode. It is dangerous, yes. You need to be careful with flames around it, but just sitting in a barrel by itself, it won't blow up. Yeah. There are some that will do that, which is not good. And you can store gasoline for long periods of time without losing a lot of it if you store it right. And it's tradable, meaning if it's storable for long periods of time, you can transport it on trains, trucks, or ships to faraway locations to trade or to power what you want. Now, the part of this that these things are what enable it to be traded and used so widespread and be a part of our society. These chemical characteristics enable it to do all of these things while being a fuel. Ammonia is toxic to humans. Pretty toxic. Also, the environment and animals.
And when you oxidize it, it becomes even worse, right? NO2, NO are very, very toxic.
Nitrous oxide actually occurs in all combustion with air, because you have nitrogen in the air, and you can form nitrous oxides whenever you burn something with air. However, ammonia does likely produce more nitrous oxide, which is not the same as carbon dioxide in terms of what it does, but it's a large contributor to acid rain, and it also has not great health effects. Nitrous oxide, when breathed in, is bad for you, among other things. So it's, it has other environmental challenges, but all combustion produces, all combustion with air produces nitrous oxide because there's nitrogen in the air.
Yeah, fair enough.
Yeah.
So far we've talked about the carbon-based ones, which are pretty much good at everything except being good for the environment.
Exactly.
The ammonia is toxic.
Yeah.
That's the only con of the ammonia.
Ammonia is toxic, so it makes it difficult to transport and store and handle. So that's kind of it's also not a super energy dense. So it's not great, but it offers a lot of the advantages of gasoline, but it's just hard to handle and toxic.
And still not great for the environment.
So it's it's like C tier or whatever you want to call it. I don't know.
Let's do a tier list.
Hydrogen is one a lot of people know about. So hydrogen, it's super energy dense. You burn it. The only byproduct is heat and water vapor. That's it. There's no environmental downside.
Where's the catch?
Where's the catch, indeed? The catch comes with how do you store it? Hydrogen is the smallest element that exists. It is just a proton with an electron revolving around it. How do you store that? I'll tell you now. You try and store it in a metal tank as like a gas. It's so small it can slip through the crystal lattice of the metal and
it
leaks through the wall. Now, also, it's so light and so small that on a macroscopic scale, when you're dealing with a tank of hydrogen, it's liquid. Sorry, it's not liquid. It's in a gaseous form. Mm-hmm. Now, trying to compress it into a liquid form, you cannot compress it. You have to cryogenically cool it. Even colder than liquid oxygen. Even colder than liquid nitrogen.
We're talking very close to absolute zero.
Not that bad, but about maybe 30 degrees above.
So you need a laser basically, because there's no other substance that is cold enough to get it cold.
No, not even. You need to just accept that you're going to lose some of it. Or you need to create a recapture system that allows you to capture this cryogenically cold gas.
You need a tank around your tank.
You need a tank around your tank. And what this means is that the people are like, well, why don't we just keep it in gaseous form? Yeah, you can. But this violates some of the very important categories that give a gasoline their advantages. You need to be able to store it for long periods of time without losing a lot of it. So if you store it cryogenically, you lose a lot of it. Also, it just bleeds through the freaking walls. It just does that. There's no material that we can do that we know of that can store 100% of it forever. It doesn't work like that. Even if you could cool it, it's just so tiny. It will bleed through the cracks. And you can make it thicker, but then your infrastructure becomes heavier. This tank you're holding becomes heavier. So you have your fuel, but the only reason you have the tank is to contain your fuel. You have a really heavy tank. Effectively, you have a really heavy fuel.
So it's not even a fuel, it's a quasi-fuel almost.
Yeah, no. It's a fuel. You can carry it with you. There are hydrogen engines. It does exist. And you can generate it from water through electrolysis. There's lots of different ways of doing it. But the point is that storing hydrogen for more than a short period of time and in large quantities is very hard. There are massive advantages to storing your fuel in a liquid state. The energy density of your fuel skyrockets if you're able to put it into a liquid form, which is part of the reason why it's done in liquid. Where liquid oxygen is so difficult to do, but that's why it's used in rockets. Making liquid hydrogen is even harder. Now, you want to transport it. You have an entire container ship. If your container ship, your one that's, let's say, normally used to carry oil, you try and carry the equivalent volume. So you just take all the tanks and you fill them up with gaseous hydrogen. Aside from the safety concerns, if you can just do that, the amount of hydrogen you're carrying versus the amount of oil you could carry it's piddly. It's absolutely minuscule. The physical mass of hydrogen that you can transport in a gas form on the same ship is so small. So by making it, in order to make it more dense, you compress it, but the advantages of compressing it are nullified by the fact that you have to have a stronger tank. You can compress it, right, at higher pressure, you store more of it, but your tank has to be stronger, so it gets thicker, so it gets really heavy. So the
same principle as before.
Yeah.
Exactly. So then you're like, okay, cool. What if I compress it and I cryogenically freeze it so it turns into a liquid so that the density skyrockets. And that is okay. That does offer very good energy density, but you have to maintain it at this cryogenic temperature of minus 200 something.
Yeah.
So that means you need cooling equipment. You need external energy. So, or maybe you siphon some of the hydrogen to use to run a heat pump to do it. And even with a heat pump, it's so hard to achieve such a low temperature, you're going to lose some of it almost. So these storage problems are the big downside for hydrogen. It burns clean, it produces water vapor, it looks cool, the burn flame has nice flame characteristics, but storing it is for long periods of time is terrible.
Okay, so gasoline, bad for the environment. Ammonia, toxic for humans.
Still bad for the environment.
Still bad for the environment. Hydrogen looks perfect, but we can't store it.
Hell yeah.
Okay, what's the solution?
And let's leave them on a cliffhanger because we have some technical problems with the camera. So let's take a little break after an hour and we'll be right back. Okay, we're back with a slightly worse camera on Slater's end, but we're back. So we were talking about metal-based fuels.
Yeah, that was the last one. So we talked about hydrogen, ammonia, and the third non-carbon fuel that we have currently is metal powders. So metal powders are a lot more complicated than the other two. They're also a lot newer, and they're not as well understood as the other two. So hydrogen and ammonia can be obtained in various ways. You can generate them even, actually. You can generate hydrogen from water through a process known as electrolysis, where you basically just stick, well, this is going to sound like I'm advocating for self-harm, but if you stick 2 electrodes into water, it will generate hydrogen through a process known as electrolysis. Now, don't take 2 prongs of home electricity and stick it into water. It's a terrible idea, but fundamentally this is the concept of electrolysis. That
is a great thing, right? Because you're making your electricity whatever way you want, the cleanest way possible, and then you're making a fuel directly out of your electricity.
Exactly. You can generate hydrogen like that. The other thing that it generates is oxygen. Now, a lot of chemical processes or industrial processes are not that bad, but it's only when they're done on an industrial scale do problems start to become evident. So solar panels are fantastic. Wait a second. What do we do with all the e-waste, electronic waste that's left over? Oh, yikes. Electric cars are fantastic. Oh shit, what do we do with the batteries after we're done? There's these problems that present themselves either if you can see that it's coming or only when it once is adopted on an industrial scale. So once again, there are no perfect solutions, only different ones. Now that being said, climate change and global warming are massive problems that we're going to have to start dealing with soon. Now, so just saying, oh, okay, well, solar panels equal electronic waste, therefore we shouldn't do it, is not a intelligent nor viable answer to any problem we have. There are technologies that we must leverage in tandem along with political and social change to effectively use different options we have available to us. Now, what I'm talking about is metal powders. Once again, I got distracted. I do that easily. But metal powders are things like iron oxide, which is rust, actually. That red stuff you see when your iron rusts, that's iron oxide. Aluminum oxide, most people don't see because it's actually just most aluminum you see, most pans or unpainted cars or any unpainted aluminum that doesn't have a covering will actually have a layer of aluminum oxide. It doesn't look like rust because of the structure of aluminum versus iron oxide. Iron oxide is rust and it will like peel and fall off, expose a new fresh iron surface, which then peels and falls off when it rusts. Aluminum oxide is solid. It generates like this coat that doesn't peel, so it stays. And so if you have aluminum pans, most of them are, I guarantee you, covered with a layer of aluminum oxide.
Something like a monolayer that we can't see.
It's very small, of course, because the oxygen can only penetrate so deep into the actual surface. But now, metal powder, how do you burn metal? Answer, actually kind of easy. Depends on you just got to apply it the right way. For example, in the space shuttle booster rockets, the two large candlesticks on the side of the space shuttle, in those solid rocket motors, remember we talked about solid rocket motors before, they're basically just fireworks, or not really, but really explosive candles. You have aluminum oxide. It's in the solid rocket engine. It's part of the fuel. You can burn it. You can oxidize it. Now, also, ancient and modern fireworks and firecrackers have metal powders in them that produce different colors when burned or act as a propellant agent. So they do exist. It does work. Now, but those are often mixed in with solids. Burning metal powders by themselves, a little bit harder. Has been done recently, though. But what you would effectively do is you cannot burn an oxide, you can burn a metal powder. So I'm going to try to be very explicit about the difference between the two of them. Aluminum oxide or iron oxide are what are called metal oxides, meaning you have a metal atom with some oxygens attached to it. You have oxidized it. Oxidization and burning are kind of the same thing. So a metal powder is just the metal by itself, no oxygens attached, meaning it has space for them. So if you oxidize this metal, if you burn this metal, you release energy in the form of heat, and your spent fuel, your used fuel, is a solid metal oxide. It's a solid. Most other fuels do not do that. Gasoline, when you burn it, produces gas. Gas is hydrogen and other stuff. If you burn hydrogen, you create water vapor. It's all gas, right?
Yeah.
So you look like you have a question.
No. But the fuel is a metal by itself, and then as soon as the fuel is used or oxidized, this is when the energy is released. Exactly. I just wanted to make sure that I followed.
Just one question right before.
Yeah.
So why aren't bikes like on the streets that are getting rusted? Why aren't they just like pew to the space? Why aren't they exploding?
Because the rusting is so slow. That's the thing. Now, it's because of you create this layer that has to oxidize, and then it peels, and then physically peels, and then you have another layer of it that slowly oxidizes. Copper oxidizes. It turns green.
Right.
Technically, the copper is burning, but the only difference between oxidization and burning is how fast does it oxidize. If it oxidizes really, really fast, it burns. If it oxidizes really, really slow, we call it rust or weathering or whatever you want to call it.
Right.
So like any metal that oxidizes, if you can oxidize it really, really fast, you can burn it. If you only oxidize it really, really slowly, it'll just look like rust. So it's really dependent upon how you're burnt and how you what shape do you make, how do you inject the oxygen, all that jazz.
Is this one of the main challenges, started with this very pure aluminum or copper or whatever metal? I think boron is one of them, and putting the oxygen in such a way that the reaction can happen very fast.
Yes. What you're actually talking about is reaction kinetics, which you guys have probably studied more than me. But reaction kinetics is how fast does this oxidization process occur, and in order for it to be useful, it has to be very fast. Otherwise, you're just oxidizing it. You're basically, your bike's just rusting. But if you could somehow oxidize all of that, the entirety of your steel bike instantaneously, it would kind of just explode and not destroy a city block, maybe not that powerful, it depends, but it would create a huge amount of heat and energy, probably vaporize most plants and grass and part of your house nearby. But that's the point, is that energy is stored in this unoxidized metal that if you could somehow oxidize it all at the same point, you can release this energy in the form of heat. Now, that's what you do with gasoline. You burn it, you release it, the energy in the chemical in the form of heat, hot gas.
Yeah.
It's the same concept. But
in this case, we start with 2 reagents, oxygen and the metal, and then we finish with 1 reagent that is still solid.
Exactly.
One product that is still solid.
Yeah,
so that's the interesting part.
This is what makes metal fuels unique, in that when you burn gasoline, when you burn ammonia, when you burn hydrogen, all of the products, everything that comes out the tailpipe is all gas. It's a gaseous form.
Yeah.
So when you have metal oxides, it's solid, meaning it'll be a powder, but it won't float off into space. It'll collect wherever your collection chamber is. Now, this leads to entirely different engine design. You cannot easily or currently use metal powders just in place of a liquid like a gasoline or hydrogen. You can't just swap them out like that. The engine design is fundamentally different because the product is a solid. There's upsides and downsides to this.
Can it produce thrust?
Thrust? Oh, yeah, sure, why not? If you can release energy and you can manipulate the energy in a sufficient way, you can do almost anything.
But it's not a gas coming out, it's heat.
Yeah.
No, you create energy. You release heat. You have hot particles. What if you transfer this heat into other gas that expands very rapidly that produces thrust?
That's very... Okay, so that's what you're talking about when you're saying a very different design of the engine. You need another gas that can be expelled from this heat.
Exactly. So energy release is a generic term that engineers use when we're talking about thermodynamics. So the transfer and trade of energy. Now, you can, if you want to produce thrust with your engine, or like a rocket engine, you're going to shoot something out the back really fast.
Yeah.
But there's no law that says the stuff that you burn and the stuff you shoot at the back have to be the same thing. So it's just, easier if they are. So I don't think metal powders are going to become a rocket fuel, besides solid rocket boosters. As a solid rocket booster, as a solid rocket engine, as a component in that, which they already are, they're very effective. So there's not really a huge impetus to make them, to try and adapt engine tech out to make it applicable in a powdered form where it flies out the back. Because it already does. It really already does in a solid rocket engine. In a firework, it already does that. It's just the design of your engine is different. In this case, there isn't even an engine. It's just a giant candle contained in a tube. And it does it all by itself. It's so simple, so straightforward. The only problem is you can't turn it off, but that's a different issue.
So it sounds like the chemistry and the science behind the oxidation of the metal fuels is already very understood.
Nope.
No?
No.
Okay.
The oxidization of most fuels is well understood. The oxidization of metal powders on a elementary level is well understood. When it comes to burning it for use in, let's say, an engine, it's not that well understood. It's a very recent thing that it's being used in a powdered form. As a solid form, pretty good, actually. That has been studied for a very long time, and it's been present in fireworks for a very long time. But burning it as a loose powder mixed with air or oxygen is very recent. And
how do we burn metal? I would have thought that when we have a metal, if we put enough energy, it'll just melt.
Well, that's the thing. See, okay, so let's say you have a bike made of steel, and you put it just into a chamber that heats up. Yeah, it'll burn. I'm sorry. You have to use the word burn very specifically. If you put it just into a very, very hot place, your steel bike, it'll just melt. And it will oxidize a little bit. But if you put your bike into another chamber where it's the regular room temperature, but it's pure oxygen in the chamber. If you take out all the air and put pure oxygen in there, it will oxidize, it will rust very rapidly. But it won't just explode. It'll happen maybe at it'll rust probably like 4 times faster than your average bike. If you remove all the paint on it, it'll rust like 10, 20, 40 times faster. So it'll be fast. You come back the next day and it's covered in scales of iron rust.
And the room is a bit hotter.
And it might be a little bit hotter, but not if you put a bunch of bikes in there, maybe. That would be a cool. That would be a cool experiment. Put a bunch of stripped paint bikes in there and see if you can heat up the room. But anyways, now, what you're really limited by is the surface area that's exposed to the air. So if you were a magician and you could take your iron bike, take off all of the paint, and remove everything that isn't steel or iron, smush it all into a ball, and flatten it out onto the floor into a very, very thin sheet of, let's say, a few atoms thick. Now, this is mechanically basically impossible, but let's say you're a wizard. You can do this. You have exposed pretty much the entire surface of this iron to oxygen at the same time. And it will all rust very rapidly because you have oxygen in the air it can touch every iron particle that it wants to all at the same time. But there's no way to do that. If it's in a bike form, your pipe, it's made of pipes, and the pipes have a thickness, right? Yeah. And in order for it to rust through the entire pipe, it takes a long time. It needs to rust, and then the scale needs to peel off. The iron oxide scale needs to peel off. Then it exposes a new surface, and that has to peel off until you can layer all the way down until you get through the pipe. And that takes a long time. But if you can expose all of the iron atoms to oxygen at the same time, then you can oxidize it all very quickly.
And go for it.
Sorry, you're just increasing the surface area then.
You're not even you have the same amount of material, but you're increasing the surface area. So that's actually a parameter that's used in powder combustion, which is surface area per unit mass. So the more surface area of your metal that's exposed to air, the faster it's going to rust. This intuitively makes sense as well. Like, more area, more oxygen, more rust. That it checks out. But, what I said was, you're a wizard, you take all the iron, you extract just the iron or steel or whatever, and squish it into a ball and then flatten it all out, and you create this very thin sheet a few atoms thick. It would be huge, number one, the sheet. Number two, how do you do that? You can't. So the next best thing is we can powder it. Yeah. Mechanically doing that is actually pretty straightforward. It's a lot easier than squishing it into an atom thick sheet. And a powder is just a ridiculous amount of very tiny balls.
Yeah.
And you have a very high you have a very high surface area on each ball, right? So you have a very tiny amount of mass in each of these powders.
A blender?
You grind it, actually. Actually, metal powders are almost like detritus. They're like a byproduct of a lot of the metallurgical industry. When you're cutting things, powder comes out. When you're grinding things, powder comes out. When you're drilling something, powder comes out. It's basically whenever you grind two things together that are very hard, one of them metal, one of them something else, you're going to tear off tiny chunks of the metal as you go through. A lot of people think of metal as like, oh, that's actually like, it's really strong, like I can't do anything. If you you can actually just bend aluminum very easily. It's all about the shape and the design of it. So my point is that in order to powder this metal, aluminum or iron is the most common one that people know about, you could just grind it. You could just grind it up and tear off little bits with your grinder, and that's it. It's very easy, actually. In comparison to flattening it out with wizard powers. Yeah. I mean, if you had wizard powers, you could just be like, wooga wooga, and it would be done. But you can't, which is unfortunate. So I want to be a wizard.
Yeah, so talking about, you were mentioning how one of the advantages of a gasoline, for example, is that it's very easily transportable, right? We can get it to different places. That would be a great advantage of metal powders as well. Right?
Yes. And that is one of the reasons why it's a good contender. It's poorly researched so far. And when I say poorly researched, I don't mean that the research is bad. That's not true. It's been very good. It's mean that it's not been researched anywhere near the same amount that other fuels have been researched. So we really don't know as much about it. advantage of gasoline, like you said, is that it can be stored without lots of energy loss for long periods of time using minimal infrastructure. So just a barrel. An oil can be stored in a barrel, and you won't lose a lot of it. Metal powder, same thing. Metal powders, when they're in a dense, compact form, meaning you just take the powder and you squish it down and stick it in a barrel, it won't oxidize. You'll get a little bit of the crusting on the surface, but if you want it to oxidize fast, you need to disperse it into air.
You don't even need a vacuum. You can put it in a barrel and maybe the top layer, like you say.
Yeah, you'll learn, like even with gasoline, it'll vaporize a little bit of it, but if the vaporization of, if you lose only a little bit of the powder over a long period of time, it's totally worth it. And like, for example, let's say you seal all this iron powder into a barrel and there's not much air left, you can only oxidize the amount of oxygen that's in the barrel. So if you don't if you can fill it up very high and there's not a lot to oxidize, it will use up all of the oxygen inside.
Fill it up and seal it. That's it.
Exactly. So as long as your seal is decent, then you're not gonna lose a large amount of it over a long period of time, both because of the compactness of it and the lack of oxygen that is in the barrel. So there we go. So and barrel is just an example. I only say barrel because oil is stored in barrels because of its specific design. With a metal powder, if you wanted to create something totally different, you could. But a big advantage of metal powder is that it can be it can be transported using the same infrastructure that we have in place for gasoline or oil, which is trains, trucks, and large tankers. And there's no limitation. We don't need cooling. We don't need, for like, let's say for hydrogen, we don't need a cooling or a high pressure tank. You don't need any pressure for metal. You just need to be able to hold it. It's gravity. It's heavy. You don't need any like special personal protective equipment or health hazards like you do with ammonia. So it fulfills those two categories very, very nicely. So it offers this big advantage there. Now, something that's really important I want to talk about with metal fuels is the energy cycle. So you talked about before with hydrogen, generating hydrogen from water using electrolysis. You said if you use green energy, it'll be good, right? That's the key. If you use clean energy to generate hydrogen from water, what you have effectively done is you have stored that clean energy into that hydrogen that you've made.
Exactly like you would do with a battery, except now it's
exactly. I mean, then you have the storage and the release and everything, but effectively you have stored your energy, and if you oxidize it later, you release that energy. So it's, of course you're going to lose some in the process. Nothing is 100% efficient, but if the efficiency is decent enough, then it's fine. Also, most engines are nowhere near as efficient as we think they are. The amount of chemical energy that's stored in your gasoline, only a fraction of it actually makes it to the wheels of your car. Between combustion, entropy,
it's like 30%,
mechanical, 30% or less easily.
Wow.
It's not, and you think, oh, 66 or 70%, that's a huge waste. Yeah, it is. But there's something called the Carnot cycle, which is like the theoretical most efficient possible cycle, and I'm not going to get into that, but basically there is a fundamental limit on how efficient an engine can be, regardless of mechanical anything.
Shout out to PhysChem1.
Shout out to PhysChem1,
if
indeed.
You know.
Yeah, exactly. So I've taken like 4 thermodynamics courses, and a lot of my study has been on, efficiency of engines and all that jazz. There are fundamental constraints on how efficient it can be. We are not near those, but let's say, like, to give you a ballpark idea, you said like most car engines today are only about 30% of the chemical energy in your fuel you start with makes it to the wheels. If you had a Carnot cycle, a perfect engine, you get somewhere near like 60 approximately.
Wow. Yeah.
There's still so much that just doesn't make it. And that's,
because in the Carnot cycle, if you had a car that had a Carnot engine, you would get to the red light, and then it would take forever to accelerate after that, because you have to accelerate ever so infinitesimally, so slowly. Right?
I mean, there's a huge host of, let's say, technical issues when it comes to that, and I could talk about engine design for a long time, but we're getting off topic.
Yeah, let's go back to
Metal
what
powders.
makes metal
Yeah.
powders, and more specifically, what makes a fuel green, and why are these carbon-based fuels not green? We just talked about why hydrogen is green. You basically take the electricity and you directly store it, but why aren't these carbon-based not green, and how can you make your metal-based fuels green?
So when you say green fuel, you mean something that does not damage the environment as in a minimal. It damages it in a minimal fashion. So one of the main ways that fuel use damages the environment and climate overall is release of carbon dioxide, along with other smaller, less desirable products like nitrogen oxide or of various kinds, or other things like that. But the carbon dioxide is the big one. The next one down that's important as a product is nitrous oxide. That's bad. And then there's a host of much smaller ones.
CFCs, etc.
Yeah. I don't know if you can produce fluorofluorocarbons from combustion. But anyways, point is that those two are the vast majority of the environmental damage that fuels perform. Regardless of we're not talking about what they're used for. If they're used in a tank, there's other damages that a tank does, but that's not what we're talking about. We're just talking about the chemical results of combustion.
So the metal powders, they wouldn't release any gas at all. Is that why they're...
Because they actually take oxygen. They capture the oxygen, and then you start with a solid metal powder, and you start with gaseous oxygen, and they fuse to create a solid metal oxide and energy. It's hot, and then that heat gets released into the surrounding air or whatever gas is surrounding it, which you can then use to do something.
And that metal oxide that you get as a byproduct, or just the product of the reaction, can you take that back, reverse the reaction, and reuse it?
Oh, hell yeah. See, this is the linchpin. This is the key to what makes metal powders a green fuel. If and only if you use electrolysis to turn metal oxides back into reactive metal powders, does it become green. If you run a generator with gasoline and use the electricity generated to turn oxides into powders, then you've just stored energy, but you've used gasoline to make it, so you've defeated the entire point of what you're doing. So only if you use a renewable energy source to store that power. You store power in the same way you store electricity and hydrogen by electrolysis. If you take metal oxides and electrolysis them to metal powders, you store the energy you put inside. Now, what energy do you put inside? Where do you get it from? That's the important question.
Yeah, that's the key element, right? If you had propane, you burn it, you oxidize it, it goes into CO2 in the atmosphere, and you had somehow a way to take the CO2 in the atmosphere and make propane again.
Yeah.
Oil would be a green fuel.
Well, there are ways to do that, but the energy and economics of it are very inefficient in terms of taking it out of the atmosphere.
It's a process that takes millions of years naturally,
and even then, propane wouldn't be considered a green fuel because you have to perform large amounts of action after the fact to nullify what you've done. So it's not because a green fuel, it has to be when you burn it, you cannot release carbon dioxide. That's kind of the general definition of green fuel.
Yeah. Okay.
Yeah. So we could of course take the carbon back from the atmosphere to make more propane, but that's the thing, you have to take it from the atmosphere. But metal powders, metal oxides, they're solid. They're powder, you can get it back, right?
There is one exception to the rule I just said, and that is biofuel. A lot of people know what biofuel is, but it's not the same thing as burning propane and taking the carbon to turn it into propane. It does kind of do that in a way where you plant some plants, the plants absorb the carbon, then you turn the biomatter into biofuel, which is then burned. But really what that does is it just trades it. It is carbon neutral per se by taking a large amount of biomass that has absorbed this carbon and then turning that into a biofuel, which then re-emits the carbon.
So the net carbon wouldn't change.
It's carbon neutral.
Yeah.
So the definition of what a green fuel is kind of depends on how strict you are with it. So biofuels, some people would consider them green fuels. Some people wouldn't. I do not consider them green fuels for the reason that biofuels, notice I didn't talk about biofuels as a non-carbon based fuel because it still is a carbon based fuel. You're just generating carbon based fuels from biomatter.
It's a renewable fuel, but it is not a green fuel.
Exactly.
Is what you're trying to say.
Yeah, that's what I'm trying to say. Additionally, a lot of the research that my supervisor did 20 years ago or so was on biofuel. But eventually the lab kind of not gave up, but they intentionally shifted away from studying biofuel because on a small scale, it's great. It's a fantastic way to recycle biomatter that you're not using. But the problems come when you do industrial scale organization of stuff like this. There's the amount of food you need to grow to then turn into biofuel is very large if you want to satisfy current gasoline demand or even a fraction of it. Now, there are people that need that food. You see the problem here.
Right.
And the huge amount of land, the incredible fertilizer and nitrogen use necessary to grow all that biomass, which would likely be corn or something else, which then instead of feeding people is going to be used to turn into biofuel, which is in the end only carbon neutral.
You can't have your fuel and then eat it.
Exactly. There's also other negative effects from industrial farming, but we're not going to get into that. That's the big thing. The amount of just land area you need to use to do it. Additionally, the production of a lot of these crops occurs in many third world countries where people they do not see direct benefit from it. This food that they're growing, it might turn, the fear is that it might turn into a modern day Irish potato famine, but instead of, it's partially political and partially because of the technological aspect of it. It would be a really weird situation where all this food that was being grown would be turned into fuel, so white liberals can feel good about their fuel use, but the people are actually starving in the streets. I'm not saying that's what's going to happen. I'm just saying that was one of the big fears of the group at the time. Not like, oh, it's going to happen. It's more just like, in the research, choosing to research this and just this, we limit ourselves to this as a potential outcome.
You steered away because large scale, it's bad socially, basically.
Exactly. Yeah. There will be, I can almost promise you, there will be terrible social effects on an industrial scale. But when you do them on a small scale, you recycle, let's say a farmer recycles his own fuel or biomass that the cut off of the stuff he doesn't use, and turns it into biofuel that he used to run his tractor, that is net zero or even less than, because you're using what would have been trash, waste biomatter that you wouldn't use.
Exactly like compost in the cities, eh?
Exactly, yeah. And it's stuff like that. Like, it really depends on, it's more complicated than just, okay, this is a good fuel, let's use it. There's really deep conversations you can have about the applicability and the social consciousness that comes along with what your fuel choice is. But, it's easy to say it's more complicated than that, but in reality it is. Like, that's it. But once again, we have drifted from metal fuels.
So
let's come back to the metal fuels. Yeah, exactly.
Metal fuels, they sound very, very promising. I mean, you can.
There are a number of fundamental limitations, but hit me with your question.
Well, yeah, that was actually my question. It's because you can store it, you can transport it, it doesn't emit gas. Of course, there's still some research to be done on it, but if it works, like, is there anything, like, what prevents it from being the perfect fuel?
It would require a shift in how we use fuel, on a psychological and a technological level. So, first off, it's not that it can be damaging for the environment and for animals and for humans. But notice how I talk a lot about iron metal powders and aluminum powders, because those are the ones that have been selected for research mostly. Metal powder generally refers to any metal powder that can be turned into an oxide, which you have a lot of them. Like the second, third rows, and even fourth rows of the periodic table have a lot of metals in them, and many of these are effective. There's a really cool graphic that I can show you, but can't show on a podcast. But the essential function is this. You want your fuel on a fundamental level to be reactive, meaning you want your metal fuel to be reactive, meaning it has to be within a certain, it constricts that constricts your chemical choice a little bit. Second off, it has to be relatively light in terms of unit weight per energy use, or per energy that it can release. So that restricts your selection again. And then also you want it to be not super toxic automatically. So that cuts out a few more. So what you're left with is about 12.
Can you name some of them and name the ones?
The two biggest ones are iron or aluminum. There's other options are zinc, magnesium. I think I saw boron at one point. And then
Copper.
Copper was another one. Lithium, potassium, sort of. Not really. It's more like an alkali. But anyways, there are multiple options, and a lot of testing was done on how fast can they be oxidized. So meaning if you can only oxidize them really slowly, they're not going to be a very good fuel.
You're done. Yeah.
So that limits your choice again. And it's kind of like a series of process of elimination, both on a technological and a large impact scale. And I'll give you the end result now. The two most promising are three actually, are magnesium, aluminum, and iron, for reasons that magnesium, aluminum, and iron oxides do exist in nature in a natural form. They also exist in your body in different quantities, of course. Iron oxide is not good to eat. Do not go lick rusty poles. But the point is, if you absorb a small amount into your system, you're not going to die. Yeah, don't go. Don't go lick rusty poles. You'll cut your tongue and get tetanus, and that's an entirely different thing. But anyways, iron oxides and magnesium oxides and zinc oxides and magnesium oxides, like some of these ones that I mentioned, are less toxic, and these are the ones that are a good thing to research, because from those groups you select the ones that are of high energy content, and then the final selection criteria is availability and economics. Now, iron and aluminum are already almost abundant in anything. I could point out like 3 things in this room that are made of aluminum. And as a result, there's a very large metallurgical industry that, as a byproduct of these processes that you use to make these aluminum and iron things, you just end up with iron powder and aluminum powder and iron oxide and aluminum oxide. And it's almost just like refuse. They don't throw it out, depends on your process exactly, but it's not what you're going for. You're not making this powder, it's just a byproduct. So you have a huge amount of it just sitting around. It means it's easily available, very cheap, not super toxic, high energy density, and it kind of fulfills these. So the ones that really fulfill that criteria are like iron, aluminum, magnesium, and zinc, sort of.
So they you end up with a product that nobody wants. There is no use for rust.
There is no
in most parts of the industry.
Yeah, aside from very specific chemical catalysis and very specific industrial processes, oxides, iron oxides, aluminum oxides are all useless in many ways.
And let's steer into how do you take these oxides and recycle them?
Oh yeah. So what you, in theory, would do is you would go to a metallurgical plant and take hundreds of kilograms of this iron oxide that they don't even want. They have to get rid of it themselves. They'd almost be happy to give it to you. Very few plants that I know of reuse their iron oxide in a meaningful way, or even collect it in a meaningful way. It's a waste product that they have to deal with. You go to them, say, I want all of this. They'll be like, shit, take all you want. We only need like a tiny amount. I don't fucking literally, please. Thank you for taking this. This makes my life easier.
We would bury this.
Yeah, I mean, don't do that, but that's the point. You have then all this iron oxide. What you do is you go back to your super special science chamber where you have rigged up a giant electrolysis vat. What that looks like is basically it's a pool. It's a pool of water. Just water, no chlorine, none of that. Just water. And in one end, you stick a metal pole. In the other end, you stick a different metal pole. And you connect them with electricity.
Yeah.
And you dump all of your iron oxides into this water, or aluminum oxide, or whatever metal oxide you're using. And through electricity, it drives this reaction that separates the oxygen from the metal, so that you end up with oxygen bubbles out of the pool, and you can collect it and do what you want with it if you want, or just let it go into the atmosphere. It's fine.
But don't you have a problem there, in the sense that you're saying that the reaction occurs in water.
Yeah.
Right. Previously, we were talking about electrolysis of water itself generates hydrogen and oxygen. Once you have more oxygen being generated than the metal that you're generating, wouldn't that make the process?
Well, if you have a huge amount of water and just a little bit of oxygen and just a little bit of metal, you're going to be generating mostly hydrogen.
Yeah.
Additionally, there's the concern if you have water and you electrolyze it, you produce hydrogen and oxygen, which they do combust. But you just have to be careful with how you do it. Now, if you put metal powder in a little bit of water and use that just as a solution to drive the reaction, you have mostly iron or whatever oxide. My answer is there are ways of doing it correctly. Like these are industrial processes that have been done for quite a long time and are pretty well understood. So getting that done is actually not a huge issue. Turning them from oxides into reactive metal powders it's done currently, but not on the scale that we were talking about.
Maybe this question is getting too much into the nitty-gritty and you won't know it and it will be okay.
Sure.
I'm wondering, how does the electricity just rips the oxygens apart from the metal?
Energy.
That's it.
Energy.
It just breaks the bond and you're good to go.
Energy is everything. So you create you have your one end of the electric pole and the other end of the electric pole. They're separated by a distance. Electrons in the one pole want to go to the other pole.
Yeah.
So they have to pass through something. On their way the short version of it is that in passing through these metal oxides, which they will do a little bit, they break the bonds between them. It's not like they just plow through and break open a barrier per se. It's more like they are absorbed by the electron structure in the iron oxides, which creates it becomes unstable enough for it to split apart, and these two elements are then they are electrically charged, and you have this gas, this oxygen, which then bubbles off up to the surface,
and it's irreversible.
While the iron remains in the bottom because it's still powder. It's still solid, right? It's the reverse of combustion, effectively.
This is why you're saying you really have to dose your water. You don't want the electrons to just go in the water from one electrode to the other. You want it to pass directly in the metal and to rip apart these bonds.
Exactly. Yeah. Every electron that doesn't do that is not one that helps you do what you want to do. So these are technical qualities of industrial processes and making them more efficient versus less efficient, but this is the general concept of what you're doing. And there are ways of doing it more effectively or more efficiently, but that's fundamentally that's what you're doing. You're using electricity to split iron and oxygen. And it can be done. It can be done very easily.
What will your research be about?
My research will most likely... I haven't actually chosen my entire thesis yet. So I don't know specifically what my research is going to be on, but what I would like it to be on is something to do with probably iron oxide or hydrogen. Both of them I find interesting, and it's something that combines my love of engineering and sustainability, environmentalism. So I find them both meaningful as options for non-gasoline or non-carbon based fuel. So I find their research worthwhile. And exactly what my thesis is, not sure. That's going to take a little bit of time, but we'll see.
You already seem very knowledgeable.
Yeah. Well, I've done a lot of reading, but yeah. So I didn't fully answer your question before, Matheus, which was what's the catch with metal fuels? Like, what makes it not perfect? There's the reason why it's being researched now is, I mean, the catch, air quotations, is that it's not well understood, which is a matter of time and research and energy and money. So that one is currently underway, that is being done. Second, the infrastructure required to recover iron oxide or metal oxides and bring them back to a dedicated facility to put into an electrolysis vat to generate this reactive powder, which can then go out again, is an extra step that most fuels do not need, where you don't have to collect the byproduct and then bring it back to a facility where they can re-energize it, basically.
You collect the oil, or you already have water.
You
or
burn the
something
oil
like
and
that.
it becomes gas, and it just flies off. And that's it,
Exactly.
and you don't need to deal with it.
So that's what you meant when you said that our relationship with fuel will have to change.
Exactly. Well, see, a lot of people think, okay, fuel, car, so metal powder, car. No, not quite. Because the infrastructure would require that all cars we'd have to make an entirely different kind of engine to use metal powder, which would then run a car in a mechanical system, not very efficiently, to collect all of this oxides, which they would then be required to collect all of that from all of the cars in a central location to ship to or transport
So
to a
you'd go to
location.
the gas station, and they would take your metal oxide in and put some
And
new
then
powder in.
powder.
new powder in, and then they would take all the ones that they collect and bring it somewhere else. And that's a huge extra infrastructure step that does not exist on an industrial scale. Not currently. It's not that it cannot exist. It's that it requires a huge stage to do it. So here's my vision for how it will be useful. Metal powders would be very useful as a long-term storage of renewable energy. If you have a power station, and then right next to it you have a electricity generation station, another one, the first one, let's say it's a hydro dam. Attached to the hydro dam, on the side, you have other facility that's dedicated to using excess electricity that's no longer on the demand in the grid, that it uses to run its electrolysis vats. And it has one giant pile of metal powder, it has one giant pile of metal oxide. And all the excess electricity is used to run electrolysis to turn your oxides into powder. You store the electricity that's not used in your powder.
Yeah.
And at peak grid time, when you need this extra oomph, you run it the other way. You burn your powder in an engine that generates electricity.
Yeah.
But that's the advantage of this, is that it's all in a central facility, no transport required, and it's a good storage of energy.
It removes the con that you've
Exactly.
that you've highlighted.
It's not that it removes the con, it's that it's applied in a different fashion. Remember I
Yeah.
said that there's pros and cons to everything, and it really, that influences how you use them.
Yeah.
So this is a perfect example of that, where if you just don't use it in cars, you do not need to deal with that step. Now, let's say you have electric cars. Where do you get your electricity from? Hydro dam, peak time, use this stored renewable energy. It all goes into the car. None of that's necessary, all that jazz. Now,
Yeah.
of course, you have the problem with car batteries and whatever, but the energy infrastructure is more feasible in this fashion. The last thing not last thing, but like something I do want to mention that's very important is that there's a big misunderstanding a lot of people have with renewable power. We as a society do not have trouble generating lots of renewable energy. We have a huge problem storing energy of any kind, renewable or otherwise, which is why gasoline is so used. It's a chemical store of energy. There are not many good long-term storage solutions for renewable power, which is why people and society have this understanding that for most people who study it a little bit, have an understanding that, wind and solar power are cyclical. So you need something to make up the difference. The only reason why you need something to make up the difference is because we don't have a good way of storing and releasing that energy for long-term on demand.
And not only is the offer cyclical, the demand is also, it changes all the time.
Exactly.
That's the biggest problem of the energy
Exactly.
industry, right?
Absolutely.
The energy industry, everyone wakes up at the same time in the morning, takes a hot shower of 15 minutes or so at the exact same time. And this is when, even here in Quebec, where we use hydropower most of the time,
Yeah.
we need to resort to some oil in those peaks of
Exactly.
energy. And this is where you come in, and we could, all throughout the year, store part of the energy we make in hydropower as basically as a metal
powder.
Metal
Yeah.
powder.
as a metal
I'm not
powder.
saying this is an option. This is what I see as, this is my personal vision of what it could be very useful for. Now, if you have, let's say you have 20 stations along the coast of Canada or along the length of Canada, you have a railway line that goes, the Canadian National Pacific, you can ship your metal powder between these stations. And in the same way you might ship oil between these stations or across the ocean. So if you have, let's say, only a handful of these, metal powder backup storage plants, you only need a few locations. You don't need to do a massive collection from cars or from airplanes where you use this fuel. You just wouldn't use it in that case, and only use it as a trade of energy that's stored in a compact form in powder. So you have, let's say, a massive surplus in Ontario, and let's say, I don't know, Saskatchewan has a peak period, some of their generators die, and they need to rely on this backup of storage. You can ship some to them, and that's it.
Wow, that's incredible.
Yeah. So we wouldn't be using that type of fuel on cars, as you mentioned.
I wouldn't recommend it. That's my answer.
Yeah.
Too explosive?
No, it's
metal
just
metal
that they
powders.
have to bring the metal oxide back.
Exactly. You have to deal with the collecting the metal oxides at the end. And it's not that it's impossible, it's that it requires a massive amount of infrastructure and coordination that does not exist currently, which is a much bigger hurdle than creating these autonomous power stations that can manipulate power.
Would it be an option though for rockets and stuff?
It already is. Like I said, it's used in solid rocket boosters.
Oh yeah, okay.
Aluminum oxide, I mean, it's not collected at the end.
Yeah.
But aluminum is used in solid rocket boosters because it's relatively light compared to many metals and has a pretty high energy density, and it burns under high temperatures very well. But yeah, so metal powders, baby. You got hydrogen, ammonia, and metal powder, and those are your three non-carbon options, ignoring biofuels.
Yeah.
So that's it.
I think Metal Powders Baby will be the title of the episode. And I think this is how we'll also end the episode. So thank you so much, Slater, for coming in.
No problem.
Thank
I love
you.
talking for long periods of time. No one stops
An
me.
amazing
That was
conversation.
amazing.
Thank you.
Thank you. Thank you for listening to Orders of Magnitude. If you enjoyed this episode, please leave us a 5-star rating on Apple Podcast and share the episode with your friends and family. If you would like to give us feedback, you can reach us at ordersofmagnitudepod@gmail.com. We would love to hear your opinions and ideas on the subject that we discussed today. Orders of Magnitude is an original project led by Philippe Carle and Matheus Schultz. The original music was composed by Vincent Ellis. Stay tuned for the next episode coming out in 2 weeks.